Hello everyone. Yeah, welcome to the invited talk session. So in this invited talk, Dr. Peng will give us the talk here. Dr. Singh, oh, sorry, I may have some echo. Okay, Dr. Singh Peng received a PhD degree in computer science from Fudan University in 2006. He is a professor of the School of Computer Science, Fudan University in China. His research interests include data-driven intelligent software development, cloud-native software, and AIOps, etc. His work won quite a number of best or distinguished paper awards, like in ICSM, ASE, ICSME, TSE, etc. He was a steering committee member of ICSME. Now he is a co-editor of JSAP, an editorial board member of Tosan, EMSE, and Chinese Journal of Software. Let's welcome Dr. Peng to give the invited talk on large-scale trace analysis for microservice architecture understanding and fault analysis. Welcome, Dr. Peng.
Okay, thanks for inviting me. I'm very happy to share our work here, large-scale trace analysis for microservice architecture understanding and fault analysis. We all know now that cloud native has been a new trend for cloud-based software applications. According to IDC, by 2022, 19% of all new applications will feature microservices architecture, and 35% of all production applications will be cloud native. Cloud native, according to my understanding, means that the design, implementation, and the deployment of an application fully exhibit the characteristics of cloud computing, for example, distributed and elastic. We know that cloud native means a series of things. Among them, I think the microservice architecture is an important part of cloud native. Microservice architecture features by small-grained services that are developed and maintained by small autonomous teams. And all the services can be independently deployed, released, deployed, and scaled. So for microservice systems, observability is very important. We all know that microservice-based cloud-native applications is quite dynamic and complex. If we want to understand the runtime behavior of a microservice system, and also try to analyze and pinpoint the root causes of runtime failures, we have to rely on the runtime observability of the application. The observability of microservice systems is supported by 3 pillars, including logging, tracing, and metrics. They support a series of observability-based applications, including business process and change understanding, runtime architecture recovery, and anomaly detection and prediction, and fault analysis and root cause localization, and also optimization of runtime deployment and configuration. So today I will share our recent work. I think centered around trace data analysis. Trace, as I mentioned just now, is an important part. Is an important part of the observability of microservice systems. Trace nowadays more and more microservice applications have adopted runtime trace pipeline for the connection and analysis of runtime traces. The microservice traces are actually initially produced by each service instance. For each service instance, it will produce some span lock. Span lock means a segment of the, means invocation between 2 service instances. So these span logs are distributed in different service instances. So first we need to connect the span logs from different service instances. Then after pre-processing, we can make, for example, we need to combine or assemble the span logs into traces and then store them in some kind of storage for further analysis. Yeah. So in this slides, we can see a trace actually is consists of a series of spans. So each span means invocation between two instances. And in popularly used tracing tools such as Jaeger, there's this kind of visualization for timeline analysis of traces. Based on this kind of analysis, we can see how the execution time of a trace is distributed. This is distributed in different parts of the traces. So this is the timeline analysis. So we know that the challenges, I think, for the trace data analysis, I think many related to the large scale, the huge volumes of data, and also highly dynamic. Also, I think trace data is very hard to be combined with logs and metrics. We know that for large scale Microservice applications, the service number can be hundreds to thousands. And at the runtime, we know that each service can have several to hundreds or even thousands of instances. So the instance number of microservice application at the runtime can be thousands to hundreds of thousands. So when in our collaboration with our industry partners, they told me that their trace number per day can be billions to hundreds of billions. That is actually very huge volume of data. And also the trace data is highly dynamic because it's produced at the runtime based on our monitoring and the tracing infrastructure. So today I will share our experience in two works. Both these two works are joint work with our industry partners. I use this. This slide shows the landscape for the observability of Microservice applications. I mentioned just now, which has 3 pillars. That is logging, tracing, and the metrics. So the first work is trace aggregation based business flow analysis. In this work mainly rely on the trace and the traces, but also we also combine some logging, the log data to connect maybe some error events, something like this. The second work is a journal work with Alibaba. It's a service dependency graph based fault analysis. So it also will use the tracing data, but try to represent the application in a service dependency graph, then use the graph to localize the root causes of specific runtime faults. So first work, this work that is the focus of this work is the trace aggregation. As I mentioned just now, the trace data is a huge volume. So the challenge here is that how to identify the useful information from the huge volume of trace data. So in this work, the basic idea is that we can aggregate the traces. So we support 2 levels of aggregation. In the first level of aggregation, we try to aggregate the traces into parses based on their trace topology. That means that if 2 traces share the same topology, which means that these 2 traces pass the same set of services and also in the same order, then we can aggregate them into one. So that is the first level of aggregation. In the second level of aggregation, we try to further aggregate the so-called parses into business flows based on key services. Key services means that a small set of key services that are essential for a given scenario. For example, in eBay, we know that there are a lot of traces that are related to, for example, online shopping. So we know that because of the business and the features of the online shopping system changes every day, so we cannot very precisely specify that what are those different kinds of traces that are related to shopping. But we can define a very small set of key services. For example, create an order and also maybe pay. That means that whatever the we don't care how the traces look like, but if a trace includes, that means if a trace parse the key services create order and all others in the same set of key services, then we regard that this trace is related to online shopping. That means that for each business, we can define a set of key services. So for all the parses that include all of the services in the set of key services, then we can aggregate them together. So based on these two levels of aggregation, we can aggregate the huge number of traces into a very small number of business flows for our further analysis. So this is overall structure of our approach. The initial input of our approach is the raw data, that is the spines. I mentioned just now, the span logs are connected from different service instances. So in the processing phase, we will assemble the spines into traces, and also we will do some repairing some traces, and then the traces we will do the two levels of aggregation I mentioned just now, and also we will identify error propagation chain. Error propagation chain means that there's a path that each service in the path maybe have some errors reported in the recently, something like this. So I think a key point here is the storage. The storage here is carefully designed for the purpose of trace analysis. We combine graph databases and analytics databases for efficient trace data analysis. We know that in some cases, we need to do a graph-based query. For example, we want to query all the traces that pass a given set of services. For this kind of queries, graph database maybe is more efficient, but in other cases, maybe we want to do some aggregation for some metrics. So for this kind of metrics aggregation, analytics database maybe is more efficient. So we combine these two kinds of database to provide efficient storage, trace data storage for our further analysis. So so you can see in our architecture, in the storage part, we include both two kinds of databases, analytics database and also graph database, to support different kind of analysis, including trace level analysis, path level analysis, and also business flow level analysis. So based on this structure, we can support different kind of analysis. So here we show the trace analysis pipeline implementation in eBay. So in eBay, this approach has been implemented as this trace analysis pipeline. We are based on the traces connected according to the open tracing standard. Then we have a pipeline. So you can see also we use Neo4j. Neo4j is a widely used graph database, and also Jude. Jude is efficient analytics database. So based on this storage, we can support different kind of analysis. We can analyze the business flow and the changes. Business flow, I mentioned just now, means something that we produced based on traces after the 2 levels of aggregation. So this business flow can show that for a given type of request, for example, if a user click a button on the client, then there's a request be sent to the server side or cloud side, and in the server side or cloud side, there's a series of server invocations. So by checking the visualization of the business flow, we can see what are the process of the what are the processing, how the request is processed in the microservice application. For example, what are the services will be invoked, and also how is the different kinds of parses. Yeah, because we know that the same type of request when the request is executed, there may be different parses because there are some branching, something like this. Yeah. Also, we can use this analysis to notice the changes. For example, the business and the development team, they will not notify the operation team about their changes. But based on this kind of visualization, you can notice that there may be some changes about the business flows. For example, you can you will find that there's a new branch. There's a new branch in a given business flow. That means different things. For example, maybe it's due to that the development team has just made a update of the in the production system. Also, it will mean something that, yeah, it means that, sorry.
Continue. Yeah, 3 minutes left. So please just, yeah.
Okay.
Continue. Thanks.
Okay, so yeah, also based on this analysis, we can analyze the error propagation chain. Yeah, so because we can connect the error count based on the logs, then we can we can combine this data about and with the business flow, then we can identify some potential error propagation chain. The second work is our joint work with Alibaba. So in this work, we use service dependency graph. Service dependency graph further aggregate the runtime trace data into a graph. In the graph, each service corresponding to one node, and the edges between services means the service invocation. For example, in the last 30 minutes, if there's one invocation from a service to another service, then there is an edge in this graph. And based on this graph, we can identify the root causes for given anomaly types. So in this work, we support three types of anomaly, including performance, reliability, and traffic. So our basic idea is that we will traverse the service dependency graph from entry node for root cause localization. So the key point here, including service anomaly detection for the single node, and also the traversing strategy, pruning strategy, and the candidate root cause ranking. So because the challenge here is how to balance the accuracy and the time, because we know that for this kind of runtime fault localization or root cause localization approach, we need to return the results in a very short time. So this balance is very challenging. So we combine different for example, we use a pruning strategy in the traversing process to reduce the time of the traversing. So conclusion, trace analysis is an important way for understanding runtime behavior and analyzing faults and failures of microservice service systems. So the challenge here is the huge volumes of data and highly dynamic and hard to be combined with logs and the metrics. So we do some exploration along this line of work together with our industry partner. And I think in the future work, we will try to consider some more intelligent trace analysis combined with logs and the metrics. And also, we want to use trace analysis for architecture recovery and balance